Hey, you are all welcome to this webinar, Calculus Everywhere, How Math Shapes the World Around You. As you've seen in the advert, today we want to see how math shapes around us, specifically calculus. I'm excited to be with you this morning. And in the next 1 hour, after warm welcome and appreciating your time this morning to join us on this interesting webinar on maths. I will introduce our special guest, the keynote speaker for today, Dr. Hamid, and he will take us through calculus everywhere. And after that, we will briefly discuss about distinction, how distinction is already teaching people about calculus everywhere, and help you to get started and Q&A. So for the benefit of those that don't know me, I'm Faiz Bashir, the CEO of FlexiServe EduSoft Limited. FlexiServe is a learning and knowledge development company. We have been in EdTech for almost 15 years now, using technology to transform education. Over the years, we've helped hundreds of schools to automate their processes, and we'll talk more about our most recent initiative, the distinction.app, later. You can join me on LinkedIn and let's connect. Our topic today, like I've already introduced earlier, this maths everywhere, and how calculus will be demystified this morning. If you are like me, who used to love maths back in the days, today is going to be an exciting refresher. But even for maths non-lovers, today is going to be, hopefully at the end of this session, you will start, loving maths, or at least being conscious about maths always around you. And this session is going to be taken by a special guest, a special friend, someone that one of the best mathematicians I've met so far. When he's talking about math, the passion in him is just contagious, explaining all the models and stuff like that. Sometimes I just smile, not really following him when he starts going advanced. But I believe today, because of the audience we have, very vast, we have probably professors in maths today, and we have maybe people that are not in the maths field completely. I'm sure by the time he breaks it down in the simplest form and is also able to show us, some of the advanced things that math is creating today, we'll appreciate his knowledge. He is Dr. Hamid A. Adamu, a passionate researcher whose life and work revolve around maths. With over 15 years of experience in teaching and research, he is with the University of Salford, where he continues to advance mathematical knowledge and its applications. He holds degree from Federal University of Technology, Yola, and proceeded to London Metropolitan University, where he did his master's, and then proceeded to the University of Salford, where he earned his PhD, all in maths. He literally breathes maths. His research focuses on fluid mechanics, mathematical modeling, optimization, and applied maths. Dr. Hamid also contributes to the growing field of maths for artificial intelligence as a senior reviewer with Outlier.ai. where he helps refine and evaluate AI-driven mathematical models. His work and passion continue to inspire others to see how math shapes innovation and the world around us. Please join me in welcoming Dr. Hamid. Dr. Hamid, you are highly welcome.
Well done. Thank you, Engineer Faiz, and everyone present today. Let me just share my screen. Allow multiple presentation. Just sharing my screen. Replace current share. Okay, replace current share. Okay, allow. Just sharing my slides.
Yeah, we can see your screen now.
Can you all see my screen? Well,
Yes.
Yes, of course.
well, I can see that it's only showing me. Wait a minute. Sorry for that. Just. You can see. But I can see. Okay. Yeah. Well done. So thank you so much, Engineer Faiz, and everyone present today. The topic of our discussion today is calculus. The topic is a very easy topic, very common, very famous, and I guess probably 99% of the audience today already heard about calculus. Probably 80 or 70 to 80% knows how to work it out on the paper, but I maybe less than 20 or less than 20% are aware of its applications in real life. So today we're going to explore some of its real applications, in our modern world. And the topic is calculus, and our title is Calculus Everywhere, How Mathematics Shapes the World Around Us. Yes, calculus is everywhere, as the topic says. Do you know that without calculus, you won't be having the modern technologies such as the smartphones, smart TV, smart watches, smart meters. Not only that, even to stream videos, video gaming. That means there would have been Netflix, Amazon Prime. There's no StarTime, no DSTV without calculus. So calculus is everywhere. So today we are going to explore how calculus serve as the brain box behind our modern innovation. And we will see how differentiation changes things and how integration accumulate quantities. With calculus, you can apply it almost everywhere in optimizing your mobile apps, in modeling epidemic diseases, and even in launching rockets. So today, we're going to look at some of its applications at the basic level. Considering the audience, there are many students, so I'll try to make it as basic as possible. Although there are complex applications as well for those who might be interested, but not for today's webinar. So calculus, we mentioned of its, some of its applications in real life, but what is calculus? You've been hearing the name, calculus, and then it can be applied, everywhere, literally. But what is that calculus? So calculus is a branch of mathematics that studies change and accumulation. That change is what we call differentiation. And accumulation is our integration. In the subsequent slides, you will be seeing all those, what is the differentiation with some examples, practical examples, likewise for integration. Calculus started a long time ago, over 400 years. It started in 1600 when Isaac Newton started to study change. Because change is, is inevitable. Change is everywhere. That's what has inspired Isaac Newton to study change. Change, as we all know that, everything changes in life. For instance, if you check our mobile phones, back in the days, there were no smartphones. There were no smart televisions. All the TVs were black and white, literally. I mean, everything is changes now. We can see now everything is, it's been modernized. In fact, not only our phones, everything changes. Even our currency, the value of our currency always changes. We all know that, and we've seen that. So, change is very important. Therefore, to study how things changes is something very important, and that inspired Newton to study that. And then later, after 70 years, around 16, a scientist, German scientist Leibniz introduced, the symbols. What Isaac Newton did was to introduce the concept of change, what we call differentiation, what we call calculus in general. And Leibniz introduced the notations, the dy, dx, and the integrals. So together, these scientists, introduced what we are using today as calculus, which can be applied in almost everywhere. Although there have been controversies that Leibniz only copied Newton, Isaac Newton, because the concept is already there. He only introduced the notations. But, with these guys, with their work, we now see how maths, how the calculus is shaping everything around us. In the subsequent slides, we can see some, practical examples. Now we said calculus is a study of change and accumulation. We said change is the differentiation. So differentiation is nothing but to study how things changes, how fast things are changing. So this is differentiation, just to study how fast things are changing. That thing could be, could be speed, could be your battery, phone battery, it could be everything, whatever that changes. So to study how things change is what we call differentiation. Differentiation measures how, for example, one quantity, you can call it y, you can call it any variable, changes with respect to another quantity, we call it x, for example. So when we hear one quantity y changes with another quantity x, we call it, the symbol is dy dx. That was what Leibniz introduced, dy dx. So that dy dx, we call it, the change in y with respect to x. Or we can call it derivatives. Or you can call it, the differentials. So I think for this presentation, I'll be calling it derivatives because there are a couple of them in the subsequent slides. It may not be dy dx, it can be db dt, it could be, it's depending on the function that you are differentiating. So, not like before, I used to think that, when, for differentiation, it's only dy dx. Whether the function is f, I thought it's only dy dx as a derivative. But, we should know that, and we can see that in the subsequent slides. If you have the function is f, for example, then the derivative will be the f dx. If the independent variable is t, you can say df dt. So you can see that. So henceforth, I'll be calling dy dx or the bdt as derivatives. I think that will help us, understand what I call. So now we've seen the definition of differentiation, how it's just to study how things changes. And before jumping into its application, let's refresh our minds on how to work it out on paper. Although I know majority of you can work that out. And then for it to be calculated, there is a very powerful rule called power rule. This power rule is the brain box behind all the differentiations in the world. Because without power rule, no function could be differentiated. Without power rule, you cannot find dy dx. You cannot find the derivatives. So that power rule, as the name indicates, is the most important, although it's very simple, but it's the most important rule in the entire calculus. We can say that is the rule that empowers everything in calculus, and calculus empowers our modern technology. So now the simple power rule says if you have y equals x to the power of n, to find the derivative of y, call it dy dx, we just multiply the function by the power, just drop down the n and subtract the power by 1. So it's n x to the power n minus 1. That's it. That's the power rule. This can be applied in every function, regardless of whatever method you're using, whether it's product, quotient rule, chain rule, wherever, there must be power rule in it. So for example, if you have y equals x squared, to find the derivative of x, of y with respect to x, or dy dx, it's just power multiplied by the variable x to the power minus 1. So 2 times x to the power 2 minus 1. Of course, 2 minus 1 is 1. So we cannot write 2x to power 1. We just write 2x because it's silently of power 1. And it's silently of, divided by 1 as well. So, and we can use the same analogy in, for example, in smartphones. You can model, for example, if you model your battery and you get this function, and modeling is something very easy. I think I've started knowing mathematical modeling when I was in Ali Mustafa College, JSS2, where you learn what's problem leading linear equations, what's problem leading quadratic equations. So this is, you can take something, model it as an equation, and then solve it. So when you model your battery phone, for example, as B of t, B standing for the battery over time. So battery as a function of time, you model it and you go 100 minus t squared. Now, to differentiate this function, now you can say the B dt, which is the changes of the battery over time, equals, we differentiate the 100, which is constant, and that gives us 0. All the constant, whenever you differentiate constant, whether it's 100, 50, million, billion, if you differentiate the constant, you always get 0. Then you differentiate minus t squared. Using your power rule, you're going to get minus 2t. So that means that, your battery drains at, with a minus 2t. When t is 1 minute, for example, is 2 minus 2 times 1, which is minus 2. That means every minute your battery will be draining by 2%. If your T is, for example, 3 minutes, in 3 minutes it's going to drain by minus 6%. So that is a simple example. And this is the animation of your battery, draining of your battery phone. For example, if your battery was, it dropped from 100 to 90 over 1 hour, then we can say that 90 minus 100 divided by over 1. If it's 2 hours, we say over 2. That means your battery dropped by 10% every hour. That means even if you have 100% in 9 hours, you will have 90% of your battery is gone. It's drained, as we can see on these animations. So we see how calculus can be applied, in your battery, in your mobile phones. Not only that, calculus also play an important role in auto brightness of your phone. We know that the smartphones of nowadays, they are adjusting their brightness automatically. Once you go into lighter, brighter light, your screen adjusts automatically. It adjusts itself. Likewise, if you moving into darker areas, it automatically adjusts itself. Just to give you just the right resolution for you to be seeing your phone. And this is the work of calculus. So what controls the brightness is the derivatives. Remember, we said that derivative is called, when we call the sensitivity S and the light L, so the SDL is the change of sensitivity as the light changes. So this is, the derivative is the one that controls how the brightness reacts to light. So when the brightness, when the derivative is so small, so we can see, for example, we make it very small, so we can see there's a slower brightness. And when you move it faster, when you make it higher, so it's a faster brightness. That makes it automatic. You don't need to be moving your finger to adjust the brightness. This is the work of calculus. Another example is, when you're downloading, so we all download maybe videos, maybe pictures, maybe documents from our mobile data, from Wi-Fi. That download rate is also the work of calculus, because we know that some internets are stronger than others. And what controls whether the internet is strong or not is the derivatives, is the change. So for example, if we let P to the download progress, T with time, so the download progress over time, we call it the PDT, which is the change of progress, the progress as time goes on, is the one is the one that controls how fast your progress is. For example, when your DP the PDT is very high, you'll be having stronger download, and when it's very weak, you'll be having slower download, as you can see here. So you can see when it's weak, maybe you're having 5, 2, 4, 6, you'll be taking 2 at a time. But when it's strong, maybe it can be jumping 20, 40, 60, 80, and 100%. Boom, you finish your download. So this is also the work of calculus. Not only that, we know that differentiation, which is calculus, can be applied in medical areas as well, medical line. I'm not a medical doctor, but those that work in medical line, they know what we call ECG, electrocardiogram. So that ECG machine uses, it measures the heart rate. So this is one of the examples of, how calculus is being applied. For example, we all know sine functions, sine functions. So when we let our function to be a sine function, maybe y is sine 2 pi. So that gives us, the wave sine, the wave, when we plot sine graph or cosine graph, it's always like this, what you can see on here. So when you adjust the derivatives, when you adjust the heart rate, when you make it smaller, so you can see the graph, the rise and fall of your heart moves, slowly, as you can see on the animation. However, if you adjust the derivatives, it moves faster, as you can see. So that means it's going 94 beats per minute, which is very high. The more you increase it, the more it goes faster. This is 173 beats per minute. I don't think someone's going to survive on this, heartbeat rate. So the average, I think, those that work in hospitals knows about 72, I think, per minute. So this is also example of how calculus can be applied, literally differentiation. And we can also apply differentiation in stabilizing room temperatures. We know that nowadays we have air conditions that automatically adjust themselves. When the room is very cold, automatically, it go off. And when it's a bit warm, it just switch on, just to keep the, as required. And this is already done by, the formula have been already given by Newton himself, which is Newton's law of cooling or Newton's law of heating. This is something very easy, very straightforward. So we can see that is the, the ambient temperature. So a practical example is, one of them is just that of the air condition. So when you adjust the room temperature, so you can see that means when the room temperature is becoming very warm, and then the air condition can go on, and when it's very cold, it just went off, just to keep the to stabilize the temperature, as the heading says, stabilizing room temperature. This is also the work of calculus. So these are a few examples of differentiation, and how we apply them in our modern world, in our day-to-day activities. Now, the second aspect of calculus is the integration, because we have mentioned that calculus is the study of how things change, which is the differentiation, and how to accumulate quantities, which is the integration. So integration is just like the anti-differentiation. It's just, the meaning is just by adding, it's just adding up the tiny bits of whatever just to get the total. It could be distance. If one walk from one point to another, if you want to find the total distance covered, you'll be adding, the smaller points in order to get your total distance covered. It could be an energy, it could be anything. Therefore, integration is just the accumulation, adding the tiny bits, summing up everything to get the total. It could be finding the area, it could be volume. So the integration literally is just the accumulation of some tiny parts. So you can see here, just all these tiny, but you want to find the area of this, you just add all the tiny parts to get the total area. And the symbol, we've seen that of differentiation is dy dx. The symbol for integration is integral of y dx, or integral of f of x dx. So that depends on the function. That integral, I think, having done further maths in my secondary school, I've first seen integral when I was in Federal University of Technology, now known as Amodi Buadam. During my Maths 101 class, our lecturer, I think Dr. Adam Walkali, was like, okay, and he was dictating to us. He was like, okay, write integral running from A to B. And I was sitting in the front. I wrote integral in words, full sentence, integral running from A to B. And he just came down and was like, okay, let me see what you guys have written. Unfortunately, I was the first person, he checked. I was like, oh, he just went back to the board. He said, when I say integral running from A to B, I don't mean you write in sentence. That means integral, you just put, the symbol. I've never seen the symbol before because I haven't done further maths. But those that have done further maths in their high schools, they know it very well. I have a friend, Tomarufu, who was very good in further maths. But then they already know it. But myself, that was the first time. So, and then students started saying that it looks like a snake. He says, yes, the best thing to use, integral is just a snake. Then we started calling it footy snake. Have you finished your footy snake assignment? Not yet. Okay, try to do that. So this is the symbol. It's just integral. Just before we dive into some one or two examples of the integration, let's get the equivalent part of the power rule. We've seen how power rule for differentiation is being used, to solve some examples, and it's the brain box behind all the other differentiation formulas. The same thing with integration. Integration, the power rule is when you have, if y is x to the power of n, just like the one we've seen before, integral of xn dx, the footy snake of xn, literally integral is the official name. Footy snake was just the name that was given about 20 years ago. So integral of xn is nothing but you just add +1 to the power and divide it by n plus 1. That's it. So for example, if your p of t is 2t, that means 2t to power 1, then the integral of 2t will be 2t to power 1 plus 1 all over 1 plus 1. That will give us 2t squared over 2. Then the 2 will cancel out. You'll be left with only t squared. So this is for the indefinite integrals. Of course, if they're definite, you can substitute the limits. So this is the formula that without it, there's no integration that is possible. Therefore, and if there's no integration, many of our modern technologies couldn't have existed. So let's look at some examples. We mentioned that integration is only to find, the total accumulation. So, and one of the examples we mentioned was the distance. It could be how, finding a distance. For example, if you want to find distance covered, maybe your speed is maybe 10 meters per second, as we can see on this animation here, maybe 10 meters per second, and you walked maybe 10 meters. To find the total distance, it's just like 10 times 10, which is 100. And then when you keep on going, when the time is like in hundreds and in thousands, the multiplication will be a bit cumbersome. So the best thing is for you to find the total distance you've covered is just to integrate, just to find the integral of your velocity. If you start from point A at time 0 and you stop at time maybe 20 minutes, and then you just integrate. Integral from 0 to 20 of v of t dt, and you apply your power rule for integration. You substitute the limit, upper limit minus the lower limit, you're going to get your total distance covered. And you get this something when you do it, manually multiplying and then per minute. This is one of the examples of where integration can be applied, everywhere, because we all walk every morning. You can walk to your school, you can walk to your class, you drive your car. So for you to find the distance covered is, it's just simple using integration. Knowing that we can also apply it in finding the total, maybe total data download. For example, you're downloading something. It could be a video, it could be something, it could be a document. And then the total data download, you can calculate that maybe in MB per minute or per second. So when the function is given as maybe R of t is 5t, for every minute at time t, your download is 5 times t. For the first minute is 5 times 1, which is 10, not 5, sorry. If after 3 minutes, you're going to have 5 times 3, that will be 15. After 10 minutes, it's going to be 5 times 10, 50, continuously. But the best thing is we just integrate. Even if the time is 1 million minutes, 10,000 minutes, for you to multiply, is a bit difficult. The easiest thing is just to integrate the function, the one you modeled, and you got 5t. And modeling is another aspect of mathematics, which is also very straightforward, very important, and very easy as well. If you know what problem, from your high schools, from your standard schools, then you'll be good in mathematical modeling. Another example of how we can move a bit. Yeah, so another example where we can apply integration is in rocket launching. Whenever a rocket is launched, there are two forces act on it. A force that pushes upwards, which is the thrust, and another force, which we know, the gravitational force, that always push the rocket downward. Therefore, for us to get the velocity, the velocity of the rocket, the speed of the rocket, because we want the rocket to reach from one point to another, for us to get the speed so that it can cover, actual target is you integrate the velocity. And how can you get the velocity? The difference between the thrust and the gravitational force, the upward force and the gravitational force. So when a rocket is launched, for example, if there is low thrust, low upward power, and high gravity, the rocket will be moving very slow because the gravitational force will be pushing it downward. However, if you increase the thrust, you put more forces, more upward forces, and then reduce the gravitational force, you can see, the rocket will be speeding higher because that red thing that we are seeing down there is the gas, because when it consumes fuel, it gives out gas. So the higher the speed, the more gas it emits. And you can model that in the moon. This is on the Earth. You can model that in the moon. You can model that in another planet, Mars. So all these are examples of integration. Let's see, come on, it's blocking me. Okay, now not only that, we've seen some simple examples of integration. And now let's give one example of a big complex one, which is not that complex, especially for the professionals. It's called application of integration in deep learning and AI. This is one of the things that we have been working on with some of our research groups in Manchester here. So, the very good concept to use the very good concept that machine learning used, AI used in that is called gradient descent algorithm. That algorithm is one of the optimization methods. It's one of the optimization techniques that that have been used even before the AI comes, because AI depends on this kind of algorithms. So before explaining these animations, let me give what gradient descent algorithm means, to a layman. So how it works is it just gets a figure, gets a number, it keep on. The main thing is to reduce the error. Reduce error. How can you reduce error in any, for example, any loss function? This is the example of loss function that's given. How can we minimize the error? This is what gradient descent does. I remember when I was doing my master's in London, that was 13 years ago. We were having a lecture on mathematical modules and methods, and the professor was giving us he was teaching about gradient descent alongside genetic annealing and gradient boosting algorithms. So he says gradient descent, we can look at it as something that we just imagine yourself as being on the top of a hill and you want to move down the hill and you're blindfolded. How can you get down the hill? He paused. And then many of us waited. Somebody who knows about air ambulance, it was like, okay, so you're going to call air ambulance to come and carry you up from the hill so that you shouldn't fall from the hill and die. It was like, well, that's not the best thing. Well, that's not the answer. How can you get down? Just imagine you're blindfolded on top of a hill. You want to go down to the bottom of the hill. How can you get down? So he says the best thing is you just take a step, take step by step. So the first step you take it towards the lowest slope. Because if you take a step and you feel that you're going a bit higher up, that means you're climbing, you're not getting down. So therefore, you should take, step, make sure that it's lower than where you were before, and then take another step, making sure that it's lower than where you were before. Continuously like that, you're going to end up at the bottom of the hill. He says this is the concept of gradient descent. This is what the computers have been feeding. They were like, okay, computer, just guess a point, keep on doing it trial by error until you get the optimum. And the optimum is with the least minimum error or no error at all. It's very difficult to get no error at all, but with minimum errors possible. So, and this is, when you work it out, mathematically, there are math behind the scene here, but this is just like to display how. Now, this is the optimum. This point that I'm pointing here is the optimum, is the target. Now, what machine learning and AI is doing is that instead of adjusting, taking one step, one step and step by step, it just automatically adjusts. When there is now when you move that, can you see that? So when you move the focus here, so the machine learning just quickly move it back so that it could be at the max, at the optimum level. And the optimum level is when the derivative is 0. Can we see that this is not exactly 0, it's just like minus 0. When you move it, that, so the optimum is when it's actually 0. Perfect. So this is the actual optimum level. That means this is where so manually you'll be doing that, keeping on, or you can write a code, keeping on reducing the error by adjusting X. But AI, they automatically, once you feed it, oh goodness. Oh, my sharing just stopped. I want to close something, it just stopped. What's going on? Share, yes. Okay, sorry guys, coming, 1 minute. So that's it. So this is one of the examples of how we can apply gradient descent algorithms in AI and deep learning. So at the minute, I'm going to play a very short video showing you how gradient descent algorithm works and how therefore machine learning works as well. So pay attention and enjoy. Most people.
Yeah, the audio, we can't hear the audio. Maybe you reshare the screen again.
I think you should reshare because you can't hear the audio except it doesn't have audio.
Yeah,
Sorry
we
guys, are
can
you saying
hear
that you
the
can hear the
audio.
audio?
Yeah, but I think just continue. Maybe I can
Okay, what can
try
I
to
do
hear
then?
you.
Because I can hear the audio from my side. What's going on? Or can I just continue playing that?
No, just go to the next slide. Think
Oh, okay.
we
Okay,
can.
that's fine then. I don't know what's wrong with you, dear. Okay, so this is, maybe you can take time when you get the link to watch it. It's something very interesting. It's just like what the professor says about climb, getting down the hill. It's something exactly like that. It's very interesting. So I think, so with that, we've seen how differentiation, explains the instant change. So when you hear the word differentiation, we just remember that it's just something about change, how things change, you know, how instant or how quick, how fast something change. And integration is how to accumulate the total distance, total whatever, total anything. So together, that means integration plus the differentiation, which make the word calculus. They are the one that power everyday tech. And we've seen that. We have seen a couple of examples. Although they are very basic, but they are the backbone because you can build on them to be solving very complex problems like the AIs. And just to give some examples, our research group in Manchester, we've used differentiation to solve, to model some epidemic diseases, the spread of diseases. I think a couple of our members are here present today. And we've used them to minimize, to develop some models, in battery that minimizes battery consumption in a D2D, meaning device-to-device telecommunication networks. And that paper, we've published a couple of papers as well, collaboratively. And we've also worked on disaster management scenarios, whereby if there's a disaster, you can deploy some devices. And we use mathematical modeling, we use in differentiation in particular to be developing the models. So with this, I can say that not only in mobile, even in the platform that we're using today, Distension, I'm pretty sure, there is calculus behind the scene. We can see very interesting, something display. I don't know much about the technical aspect, but believe me, there must be calculus. I think if they can testify that yes, there is calculus in one way or the other in developing distinction. It's something that I've never seen before. I know about Coursera, whereby you can see a course, you can enroll in a course, get your certificate, read, enjoy, get the knowledge, and get your certificate. But you cannot generate your course, you know. So, but this is, you can customize, you can generate your course. So definitely, this is change. This is like uh, advanced Coursera. So thank you so much, Faiz and everyone. Thank you so much. I think Faiz, you can take
Wow.
over.
Thank you very much. This is really, I'm seeing some comments, someone saying, this is the first time he's understanding calculus. Really, the real life applications are so great, and you'll agree with me from today, maybe so many of you that, are kind of lost. You you understand calculus, in the simplest form, and I hope it's going to be the beginning of, your interest in maths. Doctor, you can stop sharing. Let me share my screen.
Okay, let me see. Stop sharing. Wait.
Okay, yeah. All right. Let me see if the video can play from my side. The video he was about to play. Confirm if you heard the audio.
Most deep learning algorithms learn by minimizing some function.
Yes, the
You
audio
can
is
imagine
on.
this function
It's on.
like a
Yeah, thank you.
landscape, with high values represented by mountains and low values by valleys. Minimizing it is like descending all the way into the deepest valley. A natural way to do it is to always follow the steepest slope. Think of a ball rolling downhill. Gravity will naturally pull it to where the descent is the steepest. This technique is called gradient descent. Unfortunately, if there is a pit on the way, the ball can get stuck and never reach the valley. How can we help it get out of the pit? One way is to add inertia. If the ball has enough momentum, it would help it jump over the pit. This improved version is called gradient descent with momentum.
Yeah, this is the short video, explaining gradient descent in AI, and I really like that, that demo on how machine learns by trying to reduce the error. As error is being introduced, it keeps. That's what it means by learning. It tries to just, through calculation, and of course you can see it's calculus, right? It tries to reduce the error rate, and so on, using the gradient descent. As I promised you earlier, I believe, Dr. Hamid has done great justice to this topic. I look forward to, many of you developing more interest in calculus and sharing with others. And yeah, so we'll tell you how to get started, how to have access to all of these things, and so on. You can scan the QR code, follow Dr. Hamid on LinkedIn. If you are, one of the advanced mathematicians or engineers that is working on some interesting researches and has maths in it, just reach out to Dr. Hamid. He will break it down for you. You can create your own kind of group to work on interesting projects. Scan the QR code and follow him on LinkedIn. So how do you, I've seen some, we'll get to Q&A. I'm sure many of you are already excited, want to ask a few questions. We'll get to that. But I also saw some already asking how can they enroll and so on. So we'll take you through on how to do all that. First of all, if you like that animated presentation by Dr. Hamid, just scan this QR code. You can access it, play around with it, share with people, share on your social media and so on. Let more people know that calculus is everywhere. Let's make learning interesting, and exciting. Or visit dashboard.distinction.app/calculus. You'll have access to the presentation that you've just seen. Then we also have on distinction a very interesting course, very interactive, basic. Also scan this QR code to enroll to the course. You can share with your students, with your friends, anyone that is having challenge with calculus, let them just enroll to this free course on distinction.app. You can scan this QR code as well. And yeah, when you get the link to that presentation, you can also just click enroll now and you just get started. And I'm also happy to, announce that Distinction Academy is live. You can now learn anything on distinction. When we said Flexel, our vision is to truly make learning, create lifelong learners and unlock people's full potential. We are so excited today that Distinction is making this happen. With AI now, you can learn anything, and just scan this QR code. You can see the directory, the course catalog. Over 6,000 courses already exist. Go to dashboard.distinction.app/learners, share with your friends and family. Let's all become lifelong learners. Learning is now possible, for anyone. You can learn virtually anything. And if the course doesn't exist, no worries. with distinction, you can create any course you can think of. We've seen so many interesting courses on distinction, how to bake cake, how to hike, and so on. So it doesn't have to be just academic all the time. Anything you want to quickly learn about, or you want to create structured lessons to share with students and friends. And this just a short 1 minute video on how distinction courses work.
All juggling PDFs, links, slides, and scattered quiz tools just to deliver one course? With distinction, creating a complete course takes just minutes. Your content comes to life with articles, videos, flashcards, and quizzes built for better engagement. Share it with a link, no extra steps. Learners enroll and start immediately. Already use a module or Blackboard? Distinction supports SCORM and integrates seamlessly with your LMS. Whether you're a tutor, lecturer, or institution, create, share, and teach smarter. Start creating now at distinction.app/courses. Distinction Courses, made for creators, loved by learners.
Yes, you can create any course on distinction for yourself to learn anything you want, for your student, for your friends and family. So basically, like I said, you can learn anything on distinction. Just scan this QR code and start creating your courses, or visit dashboard.distinction.app/creators. You can create your course in the next few minutes. This is we also have like monetization tools for creators that want to host their courses and start earning. So just sign up and start creating your courses. Join more than 2,000 creators that have already created a course on distinction. And in general, distinction, it's a complete teaching and learning platform. It's an AI-powered teaching and learning platform that empowers creators to turn any syllabus into a full course, including notes, videos, flashcards, and quizzes in minutes. And it gives every student an AI agent that personalizes their learning. Time will not permit us to give demo, but we can create more sessions if you want to see distinction in action. There are so many interesting features that simplifies teaching and learning. We have over 100,000 students already using distinction to learn and earn. And this brings us to the end of the how to get started. And yeah, it's time for, we'll take some question in the next 2-3 minutes and we can round up. Thank you. So if you have question, just raise your hand, please, and have you on board. Yes, Godwin, let me ask you to unmute. Go ahead.
Okay. Good afternoon, everyone.
Afternoon.
Please, my question is this. I'm a chemical engineering student, and I really love, though I didn't join the lecture on time due to some network glitches, but I really enjoyed the last part of it where he was telling us about the gradients and how it can be, harnessed to solve problems. If you find yourself on a hilly place and all those illustrations, I really enjoyed them. So I've personally done calculus, and I want to know how I can harness the power of calculus in chemical engineering to make innovations, because I would like to make innovations in my field. And secondly, you introduced us to some of the potentials of distinction app. Let me not say potentials because they're already there. I've already started enjoying some of them as one of the learners in distinction app. So I want to know how I can, maximize the use of distinction app so that I can, maximize my productivity in turn. Thank you.
Okay, doctor, you can
Okay,
go
so I
for the
think the first
calculus.
question, I think the first question is addressed to me, and the second one I think is over to you, if I. Yeah, so as a chemical engineer, how can you use calculus, right? So, the simplest answer I can give is, I think distinction is a solution, because the best thing is that you can create your topic, maybe give a particular thing that you want to learn. For example, you want to learn how calculus could be used in designing maybe something that you want to use, as a chemical engineer. So you can put that prompt in distinction, and it can generate a lot of things. But the basic things is that everything, as we said earlier on, everything changes, and I'm pretty sure as a chemical engineer, what you'll be dealing with is something that is definitely not static. It's something dynamic. It changes. So you can model it, because I believe that nothing couldn't be modeled, as a mathematical model. Even if you can, you can sell something, you can model it as an equation, and then you can, with that, you can solve like over 50% of your hurdles have been solved once you get all the information into an equation. Let me call it equation, not model, so that it shouldn't sound as complex. Once you get that, if, for example, the change in something over time, you find it to be, maybe the metal that you've been using, being corrosive after 5 weeks of keeping it in moisture, you found that the metal is corrosive. And then you're like, okay, so that means that, if you keep it over time, it's going to change. And the change is for, is for worse, not for good. And then you can model it as an equation. The best thing I can say is there are lots of AI techniques already, and that will help you as a beginner with calculus. I'm pretty sure you can explore lots of it, and you can definitely enjoy it, and it will save your time in spending hours and hours reading textbooks, reading Google, searching Googles, because it can give you a narrowed solution that is narrowed to your interest. So I don't know if I've answered your question correctly, right?
Yeah, thank you, doctor. So I'll come back to your question on distinction as a general remark. Let's take more question. Mansoor.
Okay, thank you for the wonderful presentation and the opportunity given to me. Although I'm not from math major, so my worry is this calculus course open for every student? And I want to believe if it's open for all, I want to see how I will redirect it to my course of study in such a way that it will help me in addressing some calculation aspect. Thank you, sir.
Yeah, the course is open for everyone. It's very interactive and with real life examples and so on. So yeah, please share it to students and any person that wants to learn more or wants to learn calculus. Yeah, thank you. Yeah, Bulama.
Hello. Good morning. Can you hear me?
Yes,
Good
we can hear you.
morning.
Okay, good. So I did part of we did little calculus in university then a long time ago. I studied accounting, and all I can say in summary is that we didn't really like that lecturer. He used to come in and say dy dx. It was only now that I actually understood all those things he was trying to tell us. So my question is, could this also be the way in which the lifespan of things are determined? For example, you'll be told that a road would last 30 years or a building can last 200 years. Someone would think they will have to build the road and wait to see when it starts spoiling before they say, okay, this thing has been here for 70 years and this is how long it would last. Now, is it possible? Am I right in thinking that calculus should be used in determining like the lifespan of materials as well?
Yes, yeah, Mr. Bulama, the answer is definitely yes, because one of the applications of calculus is you can predict, you can predict things. And for you to predict things, that means, and the prediction, if you get all your parameters correct, all your correct assumptions, it won't be far from the truth. So definitely you can estimate the lifespan of for example, of a road. If you want to construct the road, or maybe you're building, and you want to know the weight of a lintel, or lintel, what that will carry the roof, as heavy as the roof. So all this, you can use calculus to estimate how strong the lintel would be for it to carry the roof, or how strong, what's the ratio of the mixture of cement and gravel, so that the road could last for maybe 50 years. That's why some of the buildings here in the UK, they told that, okay, this building should last for 200 years. How did they know that? They've already calculated it. They know the mixed ratio of the cement and gravel that will definitely, it will last not less than 200 years, for example. And then with that, and believe me, there's no way for it to collapse before that 200 years, because it's been tested, it's been trusted. So all this, is definitely, calculus can come in, and it could be, it can be applied straight away. So one of the things is prediction, and you can use it to predict future.
Yeah, thank you. So we have
Me.
so you can unmute. Mr. Muftau.
Oh, thank you very much. I start by appreciating the speaker or rather presenter, for a wonderful job. Hamid, thank you so much for carrying us along and for refreshing our memory. I seriously enjoyed the presentation. Far East too for coordinating. Thank you so much. The next is about a question. Before I go to the question, I am a teacher of mathematics, and I so much love the course. I really enjoyed it. In my early time, I intended to be a doctor, but by destiny, I became a mathematician. I now understand why God chose me to become a mathematician, and I'm happy for the choice. Then the question is, when you look at your animation in slide 4, where the speedometer is going from up to down, I know it's an animation, and the main idea there is to illustrate the work of the calculus. But I also wish that animation should be as accurate as possible, if my perception is correct. For example, in my elementary time or high school time, I was told, being a science student, that a moving body will contrast if the velocity is 0. But I can see from the speedometer animation there, the velocity can even reach to negative. I don't know how that can happen. I'm sorry if I'm not mistaken, or it is just a cause of animation. Thank you very much.
Okay, thank you so much, Brother Mifta. I'm just checking the slides. Although if you have it, let me just go down to it. So just as we said, this is just for this is just for animation. Let me see. Yeah, okay. I can see it, that goes down to negative. So this is just as you mentioned it. Being a professional, yeah, you mentioned it. The velocity, the least thing the velocity could take is is 0. Of course, you're right. So this is just for animation. As you can see, there was no comment on this speedometer itself. So that this is just to prove that yes, it's just for just to see the change in velocity. So there's no restriction that yes, definitely in real life, you're right. The least value equal to is 0. So this is just for animation, just to show how how things changes. And to be honest, I'm impressed by your initial wish as well. I intended to be a doctor as well. I was like, no, I have to be a medical doctor. That's why in my jump, I didn't even write mathematics. I said, I know if I write maths, I will pass it. And they will end up giving me mathematics. So I didn't even write maths in my jump. I only wrote chemistry, physics, biology, and English. But I end up, finding myself in mathematics. I was like, no, I can't do it. Okay, do it for year one, and then change to your choice. I was like, okay, I can do chemical engineering instead. And okay, finish year one. Once I finished year one, I was the highest, my CGPA was over 4 points. And then the HOD of mathematics, my then Professor Remy in Footy, he's still there in Footy. I was like, no way, you cannot change. If people like you can leave my department, who do you think, will remain in my math department? He just ripped off my application, put it in the bin, and asked me to go, to walk out of his office. That was how I stayed in mathematics. And finally, I enjoyed. Yeah, thank you for sharing your experience as well, Ms.
Welcome.
Miftah.
Thank you. Then we'll
No.
take the last question and round up. So, yeah, Babangida.
Oh,
Is
that me?
Yeah.
Thank you.
You're welcome.
Thank you, Dr. Faiz, Dr. Hamid, and the rest of the participants. Although I have joined very late due to some unforeseen circumstances, I would like to appreciate you and say thank you for giving out your time to kind of highlight and also enlighten people with respect to mathematical application in our real life day-to-day activities. Thank you very much. And
You're welcome.
we are also most hopeful that you will continue to host this kind of very beneficial programs in the future. Thank you.
You're welcome. Thank you so much, Babangida, for your kind words.
Thank you. So I think it's already almost 11:15. We are over just a little over an hour. We would like to round up here. I've seen comment from Victor, but I think we will leave that for the mathematicians to continue this conversation. He said velocity can take a negative sign since it's a vector, a speed that can't go below zero. So you can, the mathematicians, you can discuss this further. But thank you, Dr. Hamid, for your time today. And I can see, many people are excited and like the presentation. So like when we share this recording, you can visit the presentation. I can see that Dr. or Prof. Muftar is already there, and I'm sure as a maths professional, he's already sharing with his students and so on. Enroll in the course, go to distinction, start learning, be a lifelong learner. And the question, by one of the students, yes, the best way to use this, take advantage of distinction, right, is to stay engaged. We have a number of features just to make learning interactive and exciting, right? And so you have the flashcards, you have the practice question, and you now have courses. So I would say take time, learn on the courses, then use your flashcards for revision, and use the quizzes to practice. Believe you me, you just excel. And another very powerful feature is the study pal. Your AI powered tutor 247 is available for you, whether you are practicing or revising and so on. Just click the learn more and your study pal is there for you, and you can ask further questions and so on. So of course, you also earn points. As you learn, you are earning points, and you can use your points to even redeem, some valuable things on our marketplace, like recharge card and so, or get subscription on distinction platform and so on. And of course, for the lecturers as well, we have very interesting features on distinction. Create your courses. We have lecturers that have over 300 students already on their courses enrolled. just we have a course on how you can build, your courses on distinction, how you can customize it, edit it, and we have the assignment feature that can create assignments on your behalf, grade your students, assignments and so on. So just sign up today, check it out, and you'll never go back. Thank you once again, everyone, for joining. On this note, we call it a day. Bye.
Thank you very much.
You're
Wish you all the best.
Thank you. You're welcome.
Thank you. Thank you.
You're welcome.
Thank you so much, sir.